again. Here we go. Great. So we're going to jump in now to a set of slides on MCMC. And apologies, I haven't had a chance to post these to the site, but I'll hope to do so later today. Okay, so last time we took a look at this general picture, which is going to occupy us through much of the remainder of the course. And what this picture shows is two interlinked problems. On the left, we have the problem of parameter inference. Here we are trying to understand the values of parameters that are most consistent with, that best explain empirical data that's observed from the world. Sometimes that data is in the form of time series. Sometimes it's in the form of particular data points, discrete data points. But the idea is that we're trying to understand what is this data telling us about the dynamics of the underlying system through the parameters. We all know that if we take different values of model parameters, we'll see different model behavior elicited. And what we're trying to do here is to take behavior from the world and infer what are the values of the parameters that seem most likely given this data from the world. In order to do so, we're going to be reasoning about parameter space, a space where we could think of each dimension as being associated with a parameter. Maybe the dimensions are associated with beta, some probability of transmission per discordant contact, per contact between a susceptible and infective. Mu, the mean length of time till someone recovers from infection, and tau, maybe the length of the latent period. Whatever the meaning of these parameters, for a given problem, we will have typically a parameter space, and we'll want to infer values for those parameters. And a lot of the problems we're going to be looking at in the remainder of the course fall into that category. But there's going to be another problem of latent state inference, inferring if for a stochastic system, not just parameter values, but what's actually the case at any one time, recognizing that for any one realization of the model, there's a very particular trajectory of the states of the system that system will go through. And parameters won't fully specify it. Rather, we're trying to infer within those for a given set of parameters what's the underlying situation. Just how many undiagnosed infectives are there? Just how many people are there recovered, etc. So we have static parameter inference, we have a latent state inference. And last time, we talked about approximate Bayesian computation. And in an earlier lecture yet, we had talked about calibration. And each of those reflects a different approach for parameter estimates. For calibration, we're estimating the single most likely value of a parameter. For approximate Bayesian computation, we were sampling from parameters, parameter values, again and again and again, that are most consistent with the data, but in a way that was approximately Bayesian, as the very name suggests, in a way that was actually using an approximation to the posterior distribution. We'd run the model, we would assess the discrepancy between model results and empirical data, and if it fell less than a certain threshold, we would accept, otherwise we would reject. But never did we formulate a likelihood function, which is one of the most foundational elements of a true Bayesian model. So today we're going to be moving beyond that to look at MCMC, Markov chain Monte Carlo techniques. And by so doing, we will allow ourselves to be more precise about our Bayesian formulation. Specifically, we'll take advantage of Bayes' rule relating the posterior distribution with the likelihood function, and be able to sample rigorously from the posterior distribution, taking into account a prior distribution, taking into account a likelihood. But once again, we are going to be sampling from this parameter space. In calibration, we are trying to find the single most likely value. Here we'll be sampling from it. So our focus today is MCMC. So we had talked about calibration, and we had noted some of the strengths of it, but at the same time, the fact that it gives us just a single value, a single parameter vector, essentially it picks out a single point in a space where the model's behavior is closest to, in some sense, according to some metric, the observed data from the world. That is something which is limiting in some contexts. Often we're interested in bounding the model, projecting forward the results of the model, what we see from the model, and doing so with a point estimate is challenging. Even if we have confidence intervals around that point estimate, those do not translate into confidence intervals around the bounded the projection of the model. If we have a 95% confidence interval around our point estimate here, first of all, it's purely local. It's around that point. It's not considering many other points that may have just about equal fidelity to the empirical data. But more than that, that confidence interval cannot be used. We can't just take the upper part of the confidence interval, project it forward, and say that's the upper part of it going forward. The mathematics of confidence intervals don't work that way. The mathematics that give rise to confidence intervals, and neither can we take the lower part of that confidence interval. So even if we go beyond a point estimate, which is by far the most common thing to get out of a calibration, we can't really use that to project forward in a bounded way. More than that, it gives us no sense of variability in the results. And often we're interested in knowing, okay, is there another value that's almost as good, for example, in a different place within this space? Maybe we have very good matches down in this corner here or up in this corner here. Or maybe this point of this, this point of this face of the cube and that point down here. Maybe they're equally good. And we wish we could capture that in some way. After all, we have to take into account. So, in general, when we consider two parameters, say C, the contact rate, and P, the probability of transmission per discordant contact, we may have a multimodal distribution, and one that's asymmetric and one that is distinctly non-normal or non-Gaussian. An example is here, where we see this kind of hyperbolic trade-off between these. That's not surprising if they're multiplying by each other, and where we may have two regions of high probability density, one up here and one down here. It's kind of like having two peaks in that mountain range, but we have a mountain range running along here. And we'd like to be able to take that uncertainty into account. If our data suggests that sort of distribution for our parameters, we'd like to when we run the model forward, we'd like to be able to recognize that we have many competing plausible interpretations of the situation, some with high C but low P, some with high P but low C. We'd like to be able to take those into account, not put all our eggs in one basket and just say, well, we'll assume this one because it's the highest. No, we'd like to be able to take multiple ones into account. So to explore this, I want to again remind you of some notation. And once again, this notation is going to follow us through a number of lectures. Here we're going to have a set of parameters, which again we denoted by theta. For our example in this lecture, we're going to have theta be C and P, these two parameters. So the parameter vector summarizes the point in parameter space at which we're located. It summarizes where we are within this space, the coordinates within this space, as it were, the value of beta, the value of mu, and the value of tau. That's what that parameter values vector is going to give us. Now, that's the kind of current parameter when we show it in an algorithmic context. And we're going to have often a candidate parameter or a proposed parameter value, which we're going to denote as theta star most of the time. Sometimes, in an unfortunate inconsistency, it's denoted as theta tilde with a little tilde character, a little squiggle. You'll see both of those, unfortunately, in this lecture. And I apologize for that. I'm going to try to clean up the notation for future renditions, and ideally before I post these. And just as a reminder, we're going to denote observations with Y. And in many cases, we're going to have time series. So it'll be Y sub t. It's indexed by time. Now, we're going to be dealing extensively with a set of distributions going forward for Bayesian methods. P of theta is going to denote the prior distribution. Notice there's no observation considered here. We're just asking, what is our belief about the distribution of parameters? So what distribution is our best guess for our parameter distribution? Often it's subjective. We don't have a really firm understanding, but we have some reasonable guesses, perhaps, from expert judgment or from the literature or from other, from direct experience, clinical experience. This doesn't have to be privileged, but the point is it's without seeing the data which we'll be dealing with coming in, or the particular data we'll be dealing with and considering. There's going to be a likelihood function, which is, and we're going to have a probability of observing that data given a set of parameter values. And they'll be asking, what's the probability we would observe this data from the world if we had this set of parameters? After all, if we give our model a set of parameters and we run it, we're going to see some behavior. And we could then say, well, given that behavior from the model, given these parameters, what's the likelihood we would observe this data from the world? And then, of great interest, is the posterior distribution. What the data is telling us about the distribution of theta. So given the data, what's our understanding? What is our updated belief in light of the data? Take into account the prior, but take into account the likelihood function. What's our updated belief about the value of the parameters, say C and P? What's our updated belief once we've seen the data? What is it whispering to us about these parameters? Okay. So here, we're going to have a prior distribution up front. That's this one. And it's formulated prior to the observed data. And then we're going to take into account empirical data. And the goal of MCMC is to sample from, draw values from, samples from a distribution, P of theta given Y. This is our posterior distribution. We want to use MCMC to tell us what this posterior distribution is from Y. But it's not going to tell us the shape of it directly. What it's going to do is give us samples from it. It's going to sample from it again and again and again and again. And by so doing, we're going to be able to use those samples for all sorts of needs. We're going to be able to use them to run forward, to draw again and again from these samples, running forward each time. And those will be samples from the projection of the model going forward. We're going to be able to use them to find, if we want, point estimates like the median or the mean or the maximum likelihood area of the parameter space. But we can do much better than that. We can again ask, what's the probability a given intervention will yield bigger gains than another? Or we can put credibility intervals around model output, regions within which 95% of the time the actual number of cases will fall, or of hospitalizations will fall, or of hospital census. So in general, our posterior distribution is going to be messy, and we're not going to be able to look at it. We're not going to be able to just see it. We're not going to be able to draw it out. But in general, it might have many nooks and crannies and features here. And as we consider the value of the parameters, possible values of parameters, this will in general be multidimensional. It may be a very rugged surface. It may be a very involved surface. We're not going to try to draw this out. We're not going to try to reconstruct it. We're not going to try to fit it to a curve. Instead, what we're going to do is very pragmatic. We're going to draw values from it. We're going to sample from it so that the regions that are more likely will get many, many samples, and those that have low probability will have few samples. And if we do a histogram of those values that we draw from it, we should see something like this. And the more samples we draw, the better and better, the greater and greater fidelity it will offer to this. The more and more closely it will match this in all its nooks and crannies. So that's the idea here. We want to draw from values of theta in light of Y. We want to be able to draw from this distribution. And by so doing, we're going to be able to run the model forward and get credibility intervals on the results, 95% regions within which it falls 95% of the time. We're going to be able to get statistics on model outputs, say no more than 5% of the time. Do we expect the number of hospitalizations to exceed this, or the number of people overnight in the ICU or overnight in the hospital, or number of people in the ICU to exceed these values, et cetera. So that's the idea. We're going to be sampling from this. Never is this reconstructed. We just sample from it because those samples turn out to be really valuable at a practical level. So MCMC is this principled way of generating samples according to a posterior distribution. And we generate them over and over again. That's the Monte Carlo side, named after the casino in Europe, and the state that includes it. So the idea is that we're going to be drawing again and again. It's a game of chance, again and again. Now, you may be wondering, where's the Markov chain here? And again, you won't look at a Markov chain with its states and its transitions and say, there's the Markov chain. It's not reified in the algorithm. It's not, there's nothing you can point at and poke about the Markov chain. Instead, the Markov chain is implicit in the mathematics of it. And the Markov chain is indeed used to generate these samples. At any one point, we're going to be in one state, and then with a certain probability, we'll transition to another state, or we may just stay where we are. And the Markov chain will be implicit there. Okay, so high-level operation for how MCMC works here is rather simple. I think there's a chat message. So based on limitations, would we ever use the model calibration available in any logic? It's a great question. That was asked earlier. Model calibration is a bread and butter technique that is used by virtually all groups. Is it limited? It is. Often it is a pragmatic choice that we use quite a bit. We decide it's good enough for a given purpose. It's nothing about a particular package. It's not any logics or R's or technique, something that's included in MATLAB or Mathematica or what have you. That's the issue. Calibration has its purpose, its value. It tends to be reasonably cheap compared to many of these methods, reasonably inexpensive. It is something which you can formulate fairly readily, and where there are some good ways of trying to use it for both stochastic and for deterministic models. However, I do believe that the further we get into the 21st century, that we're going to increasingly see people move well beyond calibration. And there is, as we'll see in probably next time when we talk about Kalman filtering, there's some major things that calibration leaves on the table. It does not take up. One of the most important is state inference, in updating our understanding of the state of a stochastic system. Because the state of a stochastic system may be just as important as the parameters in governing its evolution. We talk about basins of attraction for nonlinear systems. We may have two different regions where the dynamics are quite different. And it matters a lot whether our state is in one area or in another area. And with the techniques we'll be examining shortly, Kalman filtering, particle MCMC, we can do much better than just estimating our parameters. And that will allow us to keep a model always updated with the latest data, not only in terms of the parameter estimates, but also in terms of our understanding of the state. It will allow us to kind of take into account our current underlying state in light of all the data that has come before. And it's my own suspicion that, if we look a decade out, a lot of the uses of calibration will have given way to some of these techniques that take into account state updating. And MCMC will be an element of those techniques, but it will need to supplement state sampling from latent states, which we'll be seeing with particle MCMC. MCMC's achieving that additional ability. So calibration by itself is limited. Calibration in methods that only sample from parameter values are limited when we think about stochastic systems more broadly. In other words, these methods that only sample from parameters, of which MCMC by itself is one. But let's try to understand it on its own terms, and then we'll see how to supplement it with additional state sampling. I should say, I speak as someone whose modeling projects they recalibrate, we recalibrate our COVID-19 model about every 2 weeks. With agent-based models, doing something beyond calibration is very performance intensive and needs to be considered carefully. I think approximate Bayesian computation is actually an excellent middle point. And we may be shifting that model eventually over to approximate Bayesian computation approach. In any case, back to MCMC. So what do we need to specify this ability to sample from this distribution, to sample over time from our parameters, our posterior distribution? Well, we need a couple things before the algorithm, and then we need keep track of some things during the algorithm. Before the algorithm, we have to decide on our prior distributions. What are our beliefs about plausible values of theta? Don't be so torn about these. As I've noted before, and as we'll see it in an exercise, often the data overwhelms the prior distribution. What the data is telling us positively screams to us compared to the whispering of the prior distribution. We also need to formulate likelihood functions. We need to decide on the form of these likelihood functions that will specify the likelihood of seeing a particular value of empirical data, a particular vector of empirical observations in light of parameters, and by extension, simulation model output. And then implicitly, we're going to apply Bayes' rule, and I'll remind you what that is in just a moment. Now, during the actual algorithm itself, during the MCMC, we'll use this Markov chain to simulate. At any one time, we'll be in a current value of theta, and then we'll consider candidates that would take us to another state, to an alternative value of theta, that would make update our current value to be this new candidate value. But sometimes we'll accept those, and sometimes we'll reject them, according to how plausible that is, and according to the relative values of the posterior distribution. Okay, so prior distribution, I've noted the basic intuition for it. It expresses a belief in values of the parameters. And we can make use of different possible parameter values, or prior distributions. One would be a uniform prior. These are sort of minimally informative priors. They don't push us towards thinking it's in one area of the space or another. For example, we might say, look, for our case where our parameters are C and P, this contact rate and the value of transmission, actually P here, I said earlier was the value of the probability of transmission per discordant contact, but that's actually not correct. I stand corrected. That, of course, we would normally denote that as beta, and I was wondering why we're using this, but no. P is actually the probability of reporting of a given case here. This is the probability a given case will be reported. Think of flu. Of all flu cases, only a small fraction, less than 1% probably, get reported. And those that do get reported are the most serious ones. through clinical measures. Through flu watch, it might be more. COVID-19, it was estimated about half of cases were reported. Excuse me, I should be careful here. Half of infections were reported. So those would become the reported cases, and the rest never got tested, went through the course of their illness, maybe infected other people and recovered. So that would be P here. So we have C, the contact rate, and P, the probability of reporting, okay, a given infection as a case. Okay, so an uninformative prior would just say, well, look, for values of C between 0 and 50 contacts per day, and P between 0 and 1, we'll assume a posterior value of 1/50 and 0 otherwise. And if you do the math, you'll find, as needs to be the case, if you integrate this up over C and P, you'll find that it integrates to 1, which is the necessary constraint on a posterior distribution. But, you know, we could use other types of distributions. And for this example, I used another one just to show the power of the data. I used one that was highly biased. And in fact, it's biased in a misleading direction. I used one whose peak would be quite far off from the actual one. And it's actually a multiplication of a triangular distribution over P. So it has a peak at 0.5, and it goes down in a linear fashion to 0 at P equals 0 and P equals 1. So it kind of says 0.5 is most likely. And where C is distributed log normally with a log mean of 5 and a log standard deviation of 2. So it's a skewed value with a long tail on the upper side. But it stretches for some distance to the right. Okay, so we've imposed some prior distribution. These are 2 of them we'll be examining, and as we'll see, it doesn't make much difference which one we assume, because the data together with the likelihood functions will overwhelm our initial assumptions in the form of a prior. Very typical with the power of Bayesian inference. Next, we're going to formulate likelihood functions. Now, remember, the likelihood functions say, what's the likelihood of observing given empirical data in light of parameters? So if the parameters were a certain value, theta, what's the likelihood we would observe a given observation factor? This is going to be very important. In fact, it's the presence of our likelihoods that's going to set this apart, MCMC, from approximate Bayesian computation. There, we were likelihood free. We accepted a candidate parameter value, theta star, if when we ran the model with it, if the model's results exhibited a discrepancy below a certain epsilon, certain small value epsilon. Here, we have a likelihood function. So we're going to specify a likelihood function. And often, but not in a required way, the likelihood function will be formulated in a multiplicative way. And so it is here. So the idea here is that we have a set of observations every 10 days. And we have 10 such observations. So we're going to have observations Y at day 0, day 10, day 20, day 30, all the way up to day 100. That's with I equals 10. And we're going to be asking about what's the likelihood that we observe a given observation, here a number of cases, in light of the a certain number of people infected and a certain reporting fraction. And this number of people reported is going to come from the model. So this is the key with using MCMC with simulation models. When you have an underlying simulation model, it can take the parameter vector theta, here C and P, you run it through the simulation model, and out you get quantities that are more directly comparable to data in the world. If we just had C and P, if that's all we had, and you were to ask me, you know, this value of C and this value of P, this number of contacts per day, this probability of reporting a given infection as a case. If you were to say, what's the likelihood of observing certain empirical data, say 50 cases on the 10th day, I would shrug my shoulders. I can't do those computations in my head. But if I have a simulation model where I can plug these in, and particularly plug in this contact rate, I can run the simulation model and see how many infections there are at day, say, 10. And then I can ask, well, what's the likelihood if I have that many from the simulation model, having plugged in the value of C from the parameter vector, if I observe that many infections, and I have a probability of reporting each infection according to P, I can compute the likelihood that I will have observed the empirical number of cases, say 50 cases. How do I do that calculation? Well, I do it with a binomial distribution. The idea of a binomial distribution, as many of you know, is quite simple. It asks, what's the probability of getting a certain number of heads if I flip a coin, potentially biased coin, a certain number of times? So if I flip a coin 100 times, and each of those times I have a 50% probability of getting a head, I could ask, well, what's the probability of getting 100 heads? It's vanishingly small. What's the probability of getting 99 heads? Well, it's a bit higher. At least I have a chance of missing one of the heads. What's the probability of getting 50 heads? Well, that's the single most likely value with a fair coin. So if the model said there were 100 people infected for the value of C from the parameter value, for this value of C, if the model said at day 10, there's 100 people infected, and if I have a probability of reporting of 50%, 50%, that is a 0.5, then I'd have a certain value of the probability of the binomial distribution for the observed data, 50. And that would be the value of my likelihood for that day. And the idea here is, of course, I don't just have one value. I have values for these different 11 observation, time 0 through time 10 inclusive. So for each of those, I evaluate a binomial distribution. The model tells me as of that day, for this parameter C, there should be this many infections. And I ask, okay, for that many infections and this probability of reporting, what's the probability, the likelihood of observing this empirical data, whatever it is, and I evaluate that. And then I multiply them all together. These probabilities are multiplied together. And that can be expressed for a binomial distribution for those familiar with your distributions in this form. This just unpacks mathematically to this. This is the form of the binomial distribution, probability distribution. So, ladies and gentlemen, this point is the key nexus between the simulation model and the observed data. Essentially, what we've done is taken our parameter vector, plugged in the values from the parameter vector into the model, run the model with it, the simulation model over time, say our compartmental model, run it over time. That will give us, for each point in time, some number of infections. And this likelihood function will compare that against the empirical data. And the likelihood function will assign a likelihood for each of these observations, which is a probability here drawn from this, our probability. It's a value, it's a probability here. In other cases, maybe a probability density, but it's some probability measure that indicates for this parameter value, what's the likelihood of, so for these parameter values, theta, what's the likelihood we will have observed this data? And we do this for each data point. Here, we just multiply them together and we get a number, right? So for a given value of theta, we get a number out that is our likelihood. Okay, now we're cooking with gas. We can plug in theta. We can evaluate the likelihood of observing the data in light of theta. And that's going to allow us to apply Bayes' rule. Because this is so critical, though, I want to see if there are any questions about this idea. So I said we take our theta, and I'll tell you where the theta will come from later. If we have a theta, I'm saying we could evaluate this likelihood of observing empirical data in light of theta, where a key part of evaluating that is running the model so that we get outputs from the model that can then be compared with the data, outputs from the model for that parameter value, theta. And then we can compare those with empirical data and compute a likelihood. Before I go on, though, to talk about how this figures with Bayes' theorem and how we turn this together with the prior into a posterior distribution, I want to see if there are any questions. So I'm going to call up my chat window, or I welcome people to speak up. Are there any questions about this linkage between the simulation model and this parameter value theta? Any questions? Okay, I'm not seeing any hands. So I'm going to take it that you're feeling at least a bit comfortable with this idea. Look, for parameters, we can run the model with those parameters. We'll get values out, and those values can be compared with empirical data. And for some values of parameters, the model's output will be probably more similar to empirical data. And for some values of parameters, it'll be poorly. It'll have a poor match to empirical data. And for any given value of theta, we get a output from the model for which we can evaluate a likelihood function. Okay, so now let's take this and apply Bayes' rule. How does this all fit together? How do we go from that likelihood function, which we've just been talking about, to a posterior distribution? Remember, that's our goal here. We want to be able to be able to see what the data is telling us about the value of parameters. We want to go from an observation about the world given the model, we want to know what is it telling us about parameter values? And we're going to be doing that through application of Bayes' rule. What would happen if the model was not in the loop? Very good question. And Ava asks, how do you compare the data? How do you compare the values? Well, these two are related questions. If a model were not in the loop, I would ask again, I mean, okay, so we say we want to find plausible values of theta. So you give me a value of theta, C equals 27 and P equals 0.035. And I want to say, how plausible is this parameter value? I want to be able to evaluate it, to critically evaluate it. Well, that's really hard just on the face of it. If you say, you know, C equals 27, there's an average contact rate of 27 people per day and a probability of reporting people of 3.5%, of reporting infection of 3.5%, I would say, you know, I don't like, and if you were to give me a time series of number of cases over being reported per day for COVID-19 or every 10 days, I would say, I mean, I can't directly evaluate from that time series what's the plausibility of this contact rate of 27 and a reporting probability of 0.035. The only way I could somehow assess the plausibility is by turning this contact rate and this reporting probability into a time series, which is what we use a dynamic model for. We plug in the value of C into some model accounts for the theory of how the infection spreads. And that allows us to then have, for every day or every half day or every 10 days, you know, some number of people infected. Now, if I then know the number of people that are infected, that's implied by CP, and I could then go and evaluate the likelihood I've observed this number of cases on a given day. So the model brings us vastly closer to the empirical data. By itself, this is kind of, you know, it's kind of opaque in terms of our ability to say how likely is certain data to be produced by this parameter vector itself. We need to plug it into a model to say, you know, what's the plausibility we would see that data from the world given this assumption of parameters. Now, Ava asked, what do I mean by compare? Well, this is what I mean by compare here. We're assessing here a likelihood as a product of probabilities. So this probability says, if we have a value of C and P, I can plug it in and get a value of I. I mean, that's what a dynamic model does, right? I plug in parameter values, I can run it. Plug in parameter values, I run, and I can get a number of infective people from the model as of any day, say day 10, with I equals 1. And given the value of P from theta, I could then say, by evaluating a binomial distribution, what is the probability? If I had that many infections, think of them as that many coin flips. And if P were, let's say, 0.5, I think of it as flipping a coin, a fair coin, 100 times. Maybe I have 100 infectives at that time from the model. Each of them has a probability of 0.5 being reported. If I flip a fair coin 100 times, what's the probability that I will observe 50 reported cases? That can be evaluated as the probability of a binomial outcome. Given that many coin flips with a fair coin, what's the probability that I report 50 cases? That's what this is. So when we say compare, this is where the comparison is taking place. between this stochastic process, flipping coins 100 times, and the empirical data. That's the comparison. And by doing this for each of the observations, day 0, day 10, day 20, day 30, that's the 10 times I here, I can get a probability for day 0 of this parameter, probability of observing the data times 0 given the parameter, multiplied by the probability at day 10 given the parameter, probability at day 20 given the parameter value. And each time, I'm using the number of infections from the model as of that day, the reporting probability, to assess what's the likelihood I will have observed that data on that day. And so there's a question here. Is it correct to say that having the model in the loop dramatically limits the solution space and therefore the computational efficiency? Yeah, you could say that. I mean, the presence of the model allows us to make that key linkage to go from the parameter value to an outcome, like some outcome we can compare to the world. If we didn't have that model, we could come up with all sorts of possible linkages, possible theories as to how the two are related, and that would be indeed a very prolific, search space. And so that, yeah, it would be, infeasible to do that, to search all possible theories. No, and instead we will typically have we will, by having one model, this will be something that would allow us to pin this down. Now, the truth is, MCMC can be applied to different models. You can actually use it to sample for models too. Now that can get quite sophisticated. It's not too bad. It's actually pretty straightforward if you have models with the same parameter space. If you have models with different parameter spaces, that gets quite complex, the theory of it. It's called, and there's a method called reversible jump Markov chain Monte Carlo techniques, which does that, which allows you to select models. But it's fairly advanced material. But sampling different plausible models is one of the uses of MCMC. You can actually select, is this an SEIR model or is this an SIR model? And which of those is most likely? You can use MCMC to sample from that, which is pretty cool. Now, Ava asks a really good question. What if the model output is continuous and not integer values? Good question. So what if I here, remember, this is coming from the model. We plug in theta, we plug in, plug in theta, we plug it into the model. C equals whatever value we're at right now. Great. And we get out, we run the model and it runs and we get out a number of people infected each time. And in general, for compartmental models, it will be continuous. So how do we evaluate this? Well, be pragmatic about it. And this is what we've done. And if you look at other publications on it, besides our own, like those from Doragati and H1N1, you'll find you do something like you round it or you round it down. So you have a continuous model, you have discrete observations. Here you have a discrete probability function and probability distribution. And so you end up taking the continuous value and you round it or round it down or round it to the nearest integer. And, honestly, it's imperfect, but other model imperfections far and away are going to be much bigger influences. So it's seen as very low concern. kind of false precision to worry about that too much, because there's much bigger uncertainties. Okay. Any more questions about that before I talk about how Bayes' theorem plays a role here? Any more questions? So great questions. I love them. Thank you for putting them forward. Okay, nothing else right now. Let's go to Bayes' theorem. So Bayes' theorem, which is very easy to prove, is of this form. It's Bayes' rule. So it relates the posterior distribution to the likelihood function in the posterior in this sort of way. Now, if this all looks like Greek to you, first of all, you can see where you can derive it immediately. If you multiply both sides by P of y here, you'll have P of theta given y times P of y, which those two multiplied, it's just the joint probability of P of theta of y. I don't know if you remember that, but P of A given B, so P of A given B times P of V, P of B is and P of A given B times P of B is P of AB. That's the joint probability distribution, P of both A and B. And here similarly on the numerator, P of theta given y times P of theta is just P of y theta, which is the same as P of theta y. It's just the joint distribution, and multiplication of just commutes, and so it's the same thing on both sides. So this is just rearranging that. But the important thing is that these are recognizable. This is the posterior distribution. That's what we want to know. It's what we want to sample from. It's what the data is telling us about the parameter values. In light of the model, of course. It's what the data is telling us about what plausible parameter values there are. This is the likelihood function. This is what we tell it. This is what we're informing it of. We're saying for a given parameter value, I can specify the likelihood of observing the data, such as in this product of binomial distributions. And this is P of theta. This is the likelihood. This is our initial belief about theta. Now, the important thing is, if we consider this as a function of theta, this is proportional to this numerator. This is just a constant. This doesn't vary with theta. So this doesn't change with theta. So if we're considering for different theta, what's the probability of different theta? It's just some constant, this thing, times this. In other words, this is proportional to this product, this numerator here. It's proportional to it. It doesn't, as we say, is this value of theta more plausible than this one, than this one, than this one? Is C really, really big and P low plausible, or is C mid-size and P mid-size plausible? The value of this right-hand side, this denominator doesn't change as we ask about different values of theta. So it's just proportional to it in terms of theta. Now, in this case, we can make use of this likelihood function that we specified here, that basically used the model as a key part, right? That's the whole trick here, is the model is the intermediary between the parameter values and the observed data. We're using the model to good effect. The model is what turns the parameter values into action, into gets us very close to things that can be compared with, apples to apples with things in the world. here we're taking out P from the parameter values in this binomial distribution. That's what takes into account the probability of reporting, not the simulation model itself. But this is the likelihood function. And then our prior distribution, well, for now, we'll make use of this uninformative prior, this uniform prior, let's say, right there. Okay, so here we have the prior distribution, here we have the likelihood function, and those map just to these. So for a given value of theta, we could use for this guy here, just this one, and this one here, it's that one. So in short, for a given value of theta, we can evaluate something proportional to the posterior distribution. That's what this is. This is the posterior distribution. We can evaluate something as proportional to that. That's awesome, because then we can sample from it, and we'll see how that goes. Okay, so what we're going to do is, if we can evaluate the value of the posterior distribution at different points, it allows us to sample from it. So some time ago, I showed you this graph here, some posterior distribution. And the point is, like, given those rules we just saw, at any point of theta, any value of theta here, I can evaluate, the height of this curve, right? I can say, what's the value at that point? What's the value at that point? What's the value at this point? You give me any value theta, I can tell you what its value is. In general, of course, there's many dimensions here. It's not just one dimension, but for simplicity and for showing it visually, it's easiest to imagine. For now, it's one distribution. So that rule I just gave you will tell you for any value of theta what the value of this is. It'll know, oh, it's quite high here. Oh, it's low there. It's low there. We can evaluate it for any value of theta using this rule. We can just this, and it's proportional to it. So there's some unknown constant we don't worry about associated with this guy, but there's basically it's we can evaluate it up to a constant at each of these places. Okay, that's great. And MCMC lets us then turn that, if we can evaluate the value up to a constant at any point here, we can sample from it. That is the amazing thing about MCMC. We can sample from this. We have a way of going and drawing values, so they're very unlikely to occur here, and they're very likely to occur here. They're not so likely to occur here, very likely to occur here, not so likely here, very, very likely, very unlikely to occur here. That's what MCMC gives us. It's a way, if we have a way of telling the value of this at every point up to a constant multiple, it will give us a way of sampling from it. That's what MCMC is all about. It will let us sample from this. And at first that may seem unimpressive, but it turns out it's really impressive. So we're going to use a Markov chain to generate these samples, to sample from this, okay? Now, again, you may say like, oh, really? Can that be that difficult? Well, if you think about it, generating random numbers, most of the time we rely on a computer to do it, so it's kind of hidden from us. But if a cumulative distribution function is known in advance, we can, for a distribution, we can draw a value from it pretty darn easily. But we normally, if all we can do is evaluate the posterior at a given point, we don't know the cumulative distribution function. We can't sample from it in that way. We have ways of kind of allowing us to sample from a uniform distribution, but in general, for an arbitrary thing where we have arbitrary values for, when I say arbitrary, I mean it will be very different for different models that we're working with. different values of the posterior distribution for different parameters, we don't have a way of formulating the cumulative distribution function and drawing from that. Instead, we need a way of sampling from it that's more general, and that's what MCMC is. Okay, so here's how it works. It's quite easy. We're going to be taking a given theta at any one time and drawing a candidate value, and we'll only accept that candidate with a certain probability. This may remind you of approximate Bayesian computation. We had a candidate value to draw from our prior distribution, and we drew it from a prior distribution. We had a candidate value to evaluate, and the question was, do we indeed emit it or not? Here, it's a little bit more involved because it's not a matter of whether we just emit it or not, it's whether we transition to that point as our new value of theta. So essentially what's going to happen is if we have a candidate, we will run the simulation model for that candidate. And we will compute the posterior. So we're going to compute the likelihood for that candidate. So if we have a candidate value, we plug in the value of P from theta star from the candidate, and we plug in C from the candidate from theta star, and we get out this, and we evaluate it. We evaluate the value of the likelihood function for the candidate value theta star. Great, great. And we can evaluate the prior distribution for theta star. Excellent. So we can evaluate this, and we get something proportional to the value of the posterior distribution. But it has this proportionality constant. So what are we going to do? Well, we're going to compare the ratio of it to the posterior at the current point theta. So we're going to be at a certain point theta. We're going to pick a candidate value we're going to pick a proposal value, and we're going to evaluate the posterior at it up to this constant, of course. And we're going to evaluate, we know what it is at our current point. We're going to take the ratio. And of course, taking the ratio of those will be invariant of this constant. It won't matter what that constant is because it'll be on both the numerator and denominator of the ratio, and it will go away. And that will leave us with a ratio of posteriors. And if that ratio is 1 or more, we'll definitely go to the candidate. If it is less than 1, well, it's going to be 0 or more. If it's less than 1, we'll flip a coin as to whether we go there. We'll basically take that as the probability we will transition, and then we'll accept or reject. So at any one time, we'll be at a certain value of theta. We'll pick a candidate. We'll evaluate the candidate relative to our current position theta. The candidate is called theta star. We'll evaluate that, the posterior there. We'll compare it to our posterior, take the ratio, and decide, do we transition or not? Or do we stick at our current place? If we stick at our current place, we'll re-emit our current value. If we transition, we'll then emit that value, and that will become our current place. Okay, so this is it in a little bit more detail. And oh my gosh, sorry, somehow my formatting got butchered in converting this to Google Slides. Okay, so we're going to pick a value for the initial value of theta. We'll draw it from some crude distribution, maybe from a prior, what have you. Okay, and then we're going to pick a candidate value. Okay, and the candidate value will be picked by picking a perturbation value. We're going to basically figure, okay, we're at some value theta, some current value theta. Okay, theta sub I. I is initially 0. We're currently at theta sub I. we're going to pick a perturbation. We're going to pick some short distance from us in some random direction. Typically, this is multivariate normal distribution centered at the current point. So we're going to pick a nearby point as our candidate. We're not going to pick too far out. We're going to pick nearby. And then we're going to, that'll be our candidate value. Okay, it's just the current point plus this perturbation. And then we're going to evaluate the value of the posterior at that candidate. That's this, again, this tilde got messed up. We're going to evaluate the ratio of these two. This is our posterior at our current point. Great. And we're going to take the posterior distribution at the candidate. Great. We're going to take their ratio. Okay. If that ratio is 1 or more, we're definitely going to the candidate. We're definitely going. Otherwise, we will be seeing if we draw a random number between 0 and 1, whether we are less than that. If so, we'll accept, otherwise we'll reject. I say that if this is greater than 1, then we're definitely going to go, because uniform from 0 to 1 will always be less than or equal to 1. And so in that case, we would accept. Our candidate becomes our new value. Otherwise, we just retain our current value. We just stay at the same place. Theta sub I plus 1 is the same as theta sub I. And then we're going to emit that new sample. Regardless of whether it's accepted or not, we're going to emit it as our sample. So if we're in a really, really good place and it drops off very quickly, the posterior around us, we're going to pull lots of values we're not going to accept. We're going to reject this one, reject that. We're just going to stay at the same place again and again and again and again. And we'll be emitting again and again and again and again the same value. And that's why it's important to pick something close to us that we have a reasonable chance of accepting. If we pick it really, really close, after all, the ratio of our posterior now to the new one will be close to 1, right? It'll be very close nearby in posterior value. And so there's a good chance this will be about 1, so there's a good chance we'll accept it. A uniform draw between 0 and 1 will very likely be less than something close to 1. And so we'll accept it a lot. If we draw something too far away, man, it may have a very poor posterior value for the candidate compared to our current one. If theta, so this delta theta, the change in theta, the perturbation, that's a vector. If it's too far away, then the posterior there may be very low to ours, and we may accept very infrequently. We'll reject frequently. Maybe this ratio is 0.1, and only 1/10 of the time will we accept. Otherwise, we'll reject. So this is the idea. And this may seem Baroque. It may seem puzzling to you. But it turns out it's really useful. Let me get rid of this darn chat window. I keep on pulling that up here. So the idea here is we're at this current point. We pick a candidate value. I'm calling theta star here, same thing as theta tilde there. That's our proposal. So if this is our current point, we pick this. Oh, look, that's a lot better than this. We're definitely going to go there. We're definitely going to go because this ratio will be greater than or equal to 1. It'll be greater than 1. And therefore, a uniform draw from 0 to 1 will definitely be less than that. So we're definitely going to go here. By contrast, if our candidate were down in this little valley, we go there fairly often. Maybe it's about 3/4 of this value. So we go there about 3/4 of this time. If we picked a value of theta star that was way down here, we wouldn't be very likely to go there at all, because this ratio will be very small. Like down here, it might be, 2%. This would be 0.02, and our chance of drawing a value that's less than or equal to 0.02 from between 0 and 1 uniformly is only like 2%. So we're not going to accept very frequently. We're going to reject, and we just stay here. We stay here. So this is the idea. We're going to be walking around here, and you could probably get a sense. It means we're going to spend a lot of time near these peaks because they're very good values, and we won't want to leave them because we'll have a lower chance of leaving them because we have a less favorable posterior value. But we will, with a certain probability, we'll transition down here, and then, we may discover this peak. And maybe the chance of going down here is not so good. It's about half of that, but half the time, if we draw this, if we're up here and we draw this value, we'll go down here. And maybe then we'd have a chance of finding this peak. And so we'll kind of, we'll transition around in this sort of stochastic way. We'll tend to spend more time on these peaks, but eventually we'll get around to exploring the distribution. So even if P of theta star is less than P of theta, we still may transition just by chance. Even if this is less than 1, by chance, we will still take it occasionally. So this balances exploration with exploitation. We'll spend a lot of time here in the peaks, and yet we will still explore some. So Maurice, yes.
Hi, David. I just posted a question in the chat.
Great. Yeah. What's a practical way to understand the ratio of two distributions? It is effectively the sum of a set to sample differences. Well, it's actually the ratio of the posterior distributions, and it's actually not two distributions. These are both in the same distribution. Like we're just evaluating the probability here, the probability here compared to the probability here. These are in the same distribution. This is the same posterior distribution. We're just saying, what's the probability or probability density at this point compared to this point? So like here, the probability density may be, I don't know, 0.05, and here it may be 0.025. Here it might be 0.0175 or something like that. And so these are different probabilities or probability densities that relate to the likelihood of falling in this region or that region or that region. It's kind of like saying, what's the probability of being within a certain area of this point compared to of that point? It's like, what's the ratio of those probabilities? And the reason we have to do it is because this is only proportional. So we need to cancel out the constant of proportionality P of y, which we don't know and frankly don't care about much, but we have to cancel it out. And so taking that ratio allows us to sort of wipe out that constant of proportionality. If this is, 3, it'll be three times this value for both theta and theta star. And so the 3 will go away when we divide the 2. I don't know if that helps at all, but it's really the ratio of probabilities or ratio of probability densities that we're looking at rather than a ratio of distributions. So you could think of it as sort of saying how likely it is that we're in, that the values in this region compared to that region. If it's very likely, we'll tend to go to that region. If it's unlikely, we won't go to that region that much. We'll stick where we are. Thank you very much. If this other region, if we're less likely to be in the region of this other candidate point. We'll still go to it occasionally. It's just we won't spend that much time there.
That clarifies it, Nate. Thank you. I somehow was understanding that we're comparing distributions and not individual.
Nope. Nope. These are all, what we're drawing out here is the posterior distribution. This is the posterior distribution. So I should probably say here, posterior distribution. Thanks for pointing that out. I will try to have that on a slide later. It was something that I said here, but I needed to say it on this slide. So thanks. We are sampling different values in the posterior distribution. And that's really what's going on here. Ladies and gentlemen, here's the irony of it. I know it's hard to get your mind around at first, but we can evaluate the value of the posterior distribution up to a constant at any point. When I say up to a constant, I mean, other than it's multiplied by a constant. We can evaluate the relative value of this distribution at any point, but we can't sample from it without having some way of doing so. And that's what this is. It's a way of sampling from it. We can evaluate at any point what the value is, but we don't want to just know what that value is. We want to draw values which are drawn from here to generate values from this posterior distribution. Because remember, at the end of the day, we want to know what is the probability of different parameters obtaining given the empirical data we see from the world and the model. What is the chance we have this value of the parameters versus that one versus that one? That's what this distribution tells us. And by sampling from it, we can get lots of plausible parameter values, right? And ones that are especially plausible will be sampled a lot. We'll get lots of them. And ones that are less plausible will sample less often. We'll get fewer of them. And by getting all these samples, we're going to be able to run this model forward in time, again, and ask things like, what's the probability this intervention yields bigger results than that one? Or what's the probability our ICUs we filled within the next month? Or what's the probability our hospital admissions will exceed this certain value? Or what's the probability, give me a 95% region within which the hospital occupancy will lie within 2 weeks' time, or what have you. That's what we can do with all these samples. We're sampling from this to get plausible values of parameters, which we can then translate into value in terms of probabilistic statements about model outcomes. So not surprisingly, this takes a lot of computational effort. From this very seat on Friday, I ran for you a approximate Bayesian computation model, and it was set to produce 100,000 samples from the distribution. And it did so using multiple cores of my machine. You may have seen them flashing down there in the lower left of the screen, again, drawing from this distribution. And so it is with MCMC. If we're running it with compartmental models, which is common, we could run it, thousands of times within a minute, if not more frequently. Now, generally, we run through what's called a burn-in period at first. So we forget about this initial value, which, is often a kind of shoddy value. It kind of pick it out of some rough value. And we run it through maybe 1,000 burn-in iterations or 10,000 burn-in iterations or what have you. And then we will sample. So, here, I wanted to show you running this in an SCIR model, and I'll see if I can give you a little example to work with in a take-home exercise. We had a true underlying value of 0.8 and a true value of C of 0.10. And here we were sampling 100,000 MCMC iterations with 20,000 burn-ins. And you could see that, here's the scatter plot. We sampled again and again and again. We got a lot of values around this region, somewhat fewer out here, somewhat fewer out yet. This is the probability of being reported as a case given someone's infective. This is a value of number of contacts per day. And so the key point is this is with a biased prior, a prior that pointed us in a different direction. It pointed us off in the wrong direction, gave us bad advice. It was off base. Maybe that's too strong a thing to say because our prior is just a belief. It's not, often we don't have a really strong reason to believe it, but it was misleading in this case. It was systematically biased. This is for a uniform prior, and you can see there's actually really not too much difference between them. Interestingly, P equals 0.8 is not quite in the center here, and I'd have to go in and find out why. By contrast, 10 is pretty much in the center. Possibly could have had a little bit to do with rounding or something like that. But you could see these two are pretty similar. In other words, the data overwhelmed the prior distribution. And having done that, we can, run the model forward and ask how many exposed individuals would there likely be at different times, for example. Here we're running the model with these sampled values. For each sample value here, we plotted it out. But in general, when we sample using MCMC, when we have these as our samples, we'll get 100,000 samples coming out of it. Great. And we could run those and we'll get a distribution for the number of people who are in the exposed state at a given at each time. And we can plot that out, and we'll see at some points in time, there's a lot of uncertainty. At other points in time, it's pretty darn certain. No matter what plausible values were found, it's pretty much died down by time 60, and certainly by time 80. This is something we can't do with confidence intervals around calibration results. We could ask, if we compare the impacts of an intervention scenario that lowers the number of people infected, and we ask, what's the difference in the number of people infected between intervention and baseline? In other words, it's number infected in intervention case versus a baseline case, intervention minus baseline. We'll see that it goes negative and then it goes positive, but not quite so much, and down. In other words, the gain from the intervention can be evaluated as a distribution induced by these sampled parameter values. All we do is we run it again and again and again and again with these sampled parameter values. And as with approximate Bayesian computation, those samples are capturing the sort of covariation that's occurring, that's implied between the parameters being sampled, say C and P. Sampling in this way performs a sort of form of sensitivity analysis, and essentially gives us some sense of how much variability is there in terms of our confidence about the output. This is telling us, at time 40, there's quite a bit of uncertainty about how much gain we will have gotten from the intervention versus the baseline. In fact, in the intervention case, there'll probably be somewhat more people infected than compared to earlier. Whereas, ultimately, very small differences between the two. So earlier, Maurice had asked about the role of the simulation model. I hope it should be obvious to you. The simulation model here serves as this critical mediator between parameters and observed data. So given a set of parameters, a theta, a value of theta, the model helps us project the behavioral consequences of parameter assumptions forward. So in other words, given a theta, it allows us to get this value of I. It allows us to turn that theta, that assumption about parameters, into outcomes that can be compared with the model. And that gives us the beachhead we need, the toe hole we need, the foothold that we need to estimate the likelihood that we observe data from the world in light of the parameters. Without a model in the way, without a model mediating between the two, how can we go from a value of C and say, what's the likelihood of observing this number of cases over time? I mean, it's a fool's errand. Without a model, we're stuck, right? But with a model, we plug that value in for C from the parameter vector. We get a number of infective people over time from the model, and we could say, aha, we have a number of infected people from the model. We have a number of cases reported in the population. If we can just have now a probability of reporting, that's the other part of the theta, then we can assess the likelihood of observing this data in the world. And that's what allows us to sample in this way. This, I should note, the simulation model can be itself sampled from. One can sample from the simulation model itself. In other words, you can sample simulation models that are more plausible, but it's much more complex if theta differs between the model, between the models. There are some practical concerns here. Burn-in time needs to be quite long. You may need to tune the parameters of the algorithm, or so-called hyperparameters. Things like the size of this perturbation size. I spoke about how this should be fairly small to get a good acceptance rate. And indeed, it's watching the acceptance rate that's one of the tricks here, tuning it. So we don't want a perturbation that's too far, because we're going to have a low acceptance rate. The posterior distribution for the candidate may be very low compared to now, and we're very unlikely to accept the candidate. This value will be very small. The minimum of 1 in that value will be small, and therefore we're unlikely, and therefore the uniform distribution draw from uniform 0 to 1 is unlikely to be less than it. Okay. But at the same time, if it's too small, we won't explore the space very, very quickly. We'll just be kind of dithering around in the region here. We won't really go very far, and it will take a very long time. So we want a Goldilocks situation. We want to have a big enough perturbation that we can start to really explore the space, but a small enough perturbation that our acceptance rate isn't terrible. And I spent too many hours of my life tuning these models in their use in PMCMC as well, for just the right acceptance rate. And it's fun, but it can take some time. Just bear in mind that acceptance rates are the key thing that has to be tuned here, and it's through that perturbation parameter. So you want something like, a good acceptance rate, something 20% or above at least, and some authors suggest 80%, something like that. Okay, a few other practical concerns, and we'll break. High covariance between parameters. If you have two parameters and they exhibit high covariation, if you had C and beta, for example, and they were multiplied by each other, this high covariation between them, and it tends to lower efficiency. And there's some ways around this, but it will often require a lot more samples if you don't do something explicitly about this. And a final thing I'll just note is there's a need typically here to assess the convergence of the algorithm. When we perform MCMC, a lot of our attention is on acceptance rate and convergence, making sure the Markov chain is well mixed, making sure we're exploring the space well and efficiently, and we're not spending undue time just sitting at certain places. We're getting really good mixing. Getting that convergence requires tuning the acceptance rate in ways that can be a bit of an art. Yeah, and I'll just say there's many MCMC algorithms. So MCMC is what's called a batch or offline Monte Carlo algorithm. We take all the data at once. And what we're going to be going to next, actually, is a class of algorithms that are online algorithms. They take data as it unfolds over time and takes this data into account in terms of giving an updated estimate of the system. We don't have to go back and process all data to this point, just the new data. We're going to see probably on Friday Kalman filtering, which is kind of the first method in this regard. But then we will be turning to particle filtering, which is a much more sophisticated technique yet. Okay. So MCMC approaches provide more general alternative to calibration. They're really best suited to deterministic models. MCMC allows for greater robustness in conclusions in light of parameter uncertainty. And if we're dealing with stochastic models, sequential Monte Carlo methods and particle filtering or Kalman filtering on the cheaper side are both options. If you want to estimate both parameters and state, inevitably for a stochastic system, use PMCMC. A PMCMC takes what you learned today with MCMC, combines it with particle filtering in a very savvy way, and then uses that to sample jointly from the distribution over parameters and state of a system. So that's all we have for today. Thank you very much for your patience. And I'm going to stop the recording here, and we will go and, a question a student asked, what effect does noise have on processes and outputs? That's going to be a central part of our handling of stochastic systems with particle filtering and particle MCMC. Normally, MCMC is most commonly done with deterministic systems. If you're having noise present, you really want to, in general, make use of a method like Kalman filtering or particle filtering that will take into account what's called process error. So that's where there is noise in the evolution of the process, and we'll see some of that next time. Okay, so that's all for now.